the two events E and F are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are independent are dependent. Two events are dependent if the occurrence of event E in a probability experiment affects the probability of event F. And I'll explain it in a simple example in just a second. So just put it in plain English. You agree that if I flip a coin 5 times, the first 4 flips does not affect the 5th flip, right? Even though it feels like it, right? Let's say I get 4 heads in a row, it feels like the next one should be tails, but that's BS. Each event is independent. So that means that no matter what happens before, the next flip is just still 50%, right? You go to play roulette table in Vegas, you get black over and over again. You feel like the next one might be red, but it's not true. It's not how it works. But it's a very common thing to believe, okay? Now, alternatively, let's say you're drawing cards, right? Each time you draw a card, you agree that there's less cards in the deck. So now the next draw have a different probability from the first draw because the deck is smaller. So those events would technically be dependent. Okay. See the difference? So if each event somehow affects the other one, then dependent. They're separate, there's no effect. Independent. That's the only difference. Okay, let's think of an example here. Suppose you flip 2 coins. What is the probability of getting heads twice. So first of all, what is every possible outcome? Flipping 2 coins. Yeah, we can get heads twice, right? What else? Heads tells, okay. Tails tells. As we're talking about, technically, the event tells heads would be different. Because it happened first, right? You get a tells first, then a heads, or heads first, and then a tells. Even though that's technically the same, they are two different events. It's kind of like rolling a 7. 3-4 versus 4-3 is two different events because one die could be a 3. Or in the next attempt, that same die could be a 4. See what I mean? Even though it feels like the same thing. Two different events. Anyway, so there's a sample space, every possible outcome. So the probability you can see, if you just count them, it's just one way to do it. Out of how many? That's 1 out of 4. So you can just figure it out by counting them. But if we use this idea of multiplication rule says, let me find the formula first. So that's the answer, but using the new rule. For independent events. If E and F are independent, then the probability of E and F, or the probability of E intersected with F, is equal to probability of E times the probability of F. So that's your multiplication rule. Now, what's the probability of getting 1 heads? 1/2, right? 1 out of 2. So if I wanted to happen again, it'd be a 1/2 times a 1/2. Because those events are independent. Does that make sense? Which is a 4th, which we already knew. So probability of heads and heads is equal to the probability of heads times the probability of heads, which is a 1/2 times a 1/2. That makes sense? Get a heads first, then the heads again. You think of them as two separate events. The first flip does not affect the second flip, therefore they are independent. So you can use multiplication. So if you're independent, you can always do this. Okay. Or another example would be, what is the probability of getting heads and then rolling a 6? Suppose I have a coin and a single 6-sided die. Those things are separate, right? The die does not affect the coin. You would do the same thing. Let's go ahead and do it just for fun here. Suppose you flip a coin and roll a 6-sided die. What is the probability of getting heads and 6. So the question is probability of heads and 6. So that's the same as saying P of H times P of 6, because they are independent. You can just do this. So probability of getting a heads is 1/2, right? What is the probability of getting a 6? 1 out of 6. So with both these to happen at one time, that would be 1 out of 12. So for that event to happen at the exact same time, it'd be 1 out of 12. So you can see that the chances go down, right? And if you think about I don't know, let's think about multiple choice tests, right? Each question has 4 options. If you guess on all of them, there's the chances that you're going to get 100%. So each time it'd be 1/4 chance times a fourth times a fourth. You see how that statistic drops quick, right? It's not going to happen, right? Getting 100% on pure guesses, it'd be an incredibly small decimal. It'd be one. That's if you have 20 questions, it'd be 1 out of 4 raised to the 20th power. I don't know what that is. So just for fun, right? Let's pretend you have 20 questions and you guess A, B, C, D, the whole way down. The chance of it getting 100% would be this. So 13 zeros in front of the 9. It's getting close to like lottery levels. Anyway, any questions on the multiplication rules? Does that make sense? Do you see if they're separate? Just multiply. Okay. And this is true for n events. So if you have, like I just said, right? If you have 20 questions, that would be 20 events. Event 1 being question 1. Event 2, question 2. Okay, or event 1 being coin flip 1, coin flip 2, etc. Okay. You guys cool on the first page? So, any questions on that idea? Okay. Example 3. Suppose you roll a 6-sided die. What is the probability of getting at least 4? What does at least mean? 4 and above. So this question is actually saying, what is the probability that x being the outcome is greater than or equal to 4? Does that make sense? Whenever you hear at least 4 or more. You hear at most, then it'd be 4 or less. Okay. So this would be, well, you can think of this in 2 different ways. Probability of 4 You can just do them all separate, add them all up, 4, 5, 6. Right. You can also do this idea of complements. See, would that work here? It would, but it wouldn't be interesting. What's the chance of getting a 4? And 5 and 6. Same thing, right? Let's add them up. So that would be 3, 6, which is 1/2. Here's a question from the book. Compute the probability that at least 1 male out of 1,000 aged 24 years will die during the course of the year. If the probability that, how do I phrase this? That the 24-year-old survives is 0.9986. So what's the probability that 1 out of 1,000 24-year-old males will die throughout the course of this year if the statistics are that they'll survive at a rate of 0.9986? So you can use complements here to help you out. Okay, so you hear that word at least 1. The probability that at least 1 dies. That's equal to 100%, meaning 1, minus the probability that nobody dies. So you'll complement, right? So 1 minus nobody dying versus 1 died. 1 or 4. And survival rate with this is being okay. This would be 1 minus 0 point. Well, actually, hold up. Let me think about that. So this statement is true. But if none die, then that means the first survived, second survived, all the way to 1,000, right? So we can consider each of those an event. So that would be 1,000 events, 1,000 males that are 24 that did not die. So one of them surviving would be 0.98. But I have to do it 1,000 times because it'd be 1,000 events. Does that make sense? So no one dying means let me put some more details. First survives. And second survives. Don't have enough space, guys. I'm sorry. It's looking like garbage. I'm gonna put it way over here. None dying means that they all survive. So the first guy survives, and the second survives, and all the way to 1,000. That clear? Why we have the 1,000 power? It's because of this. So that'd be 1 minus each of them surviving. So the chance of the first one surviving, the second one surviving, third one, so each one is an event. So nobody dies. The chances of that happening would be 1 minus 0.9986 to the 1,000. So I want to add an extra detail for you, just in case. So calculate this. It's probably that at least one person dies from that age group. That probability for one person would be 1 minus this to the 1,000. So what is that? I don't know. .75. Is that what you guys got? Seems pretty high, right? Do you see why though? Does that make sense? The logic? This is one or more, meaning one could die, two could die, three could die, all of them could die. As long as any of those events happen, then at least one died, right? So it should be pretty high. Anyway, any questions with the at least problem? Is it clear?
So that's what that means. Questions we would want to consider each event as different independent events. Correct?
Yeah, it should be used for those times. If you see the word at least one, then remember you can use this idea here. At least one means 1 minus probably one. What is your whatever? Okay, let's look at the homework. That's about it for 5.3. Simons. There it is. Okay. First question is just definitions. So question 6, when they start actually having calculations. Said E and F are independent, then you would just multiply it together, right? So E and F means they're both having the same sign, so 1 or question 6, that's all you gotta do. Now, if they're dependent, you cannot use multiplication rule. Here, these are independent, right? Obtaining 6 tails in a row when flipping a coin. So it'd just be one half to the 6, because it'd be 1/2 times a half times a half, 6 times. Anyway, let me know if you get stuck. It doesn't seem too horrible. We'll see.